All right, guys. So we have an elevator, 650 kilogram elevator, starts from rest down here and moves upward for 3 seconds with constant acceleration until it reaches a cruising speed of 1.75. All right, what's the average power for the elevator motor during this period? Okay, so there's a couple things you got to calculate with a kinematic. There's no way around it. You just have to go back to chapter 2 and use the kinematic. So for example, we're going to need the acceleration in this period. What's the acceleration? Actually, I take that back. You don't have to have the acceleration here. I'm going to show you two ways to solve this, but one of the ways requires the acceleration. So using a kinematic, you get an acceleration of 0.5833 meter per second squared. How did I get that acceleration? I just used VF equals V initial plus AT. V initial is 0. The only thing missing is A. So you can solve that for acceleration. The other thing we're going to need is how far the elevator moved. So what is this displacement for this first part? So the first part is the acceleration. Okay, then what's the second part going to be? The elevator keeps going. What's going on up here? What's the acceleration up here? 0. Oh, I love that website. All recipes. I'm really into cooking right now. Okay, so the second part is 0 acceleration. So we got to find out what is this displacement for the first part of the problem. So using a kinematic, I used x equals 1/2 VF plus V initial times T. V initial again is 0, and we have time, and we have V final. So this displacement comes out as 2.625 meters. That's how far the elevator goes for the first part, okay? Now I'm going to show you two ways that you could solve part A. What is the power of the motor during the acceleration period? So let's look at power this way. So there's two ways to look at power. You could say power is work per time, and then what's the other way you could look at power? You could say that power is what? Energy per time. Both of those are joules per second, right? What do we measure work in? Work is what? Joules. What's time? Second. What's a joule per second? That's called a watt. Guess what? Over here? What is energy? Joules. What's time? Second. What's that called? A watt. So look at, you can solve this problem either way. You could look at it from the work perspective or the energy perspective. Okay? So let's do it. Let's start with the first way. Work per time. Power equals work per time. Well, guys, what are we trying to find the power of? The power of the what? What is the average power of the motor? So let's call it that. Power of motor, well, that's going to be equal to what? The work of the motor divided by time. Okay? Well, what's the basic work equation? Work is what? Force times displacement. What force is that going to be? If we're looking for the work of the motor, then this needs to be what? Force of the motor. You guys are so quiet. Okay, so look, do we have delta x? Yeah, what's the delta x? That's this. That's how far, that's the distance that the force of the motor acts for, 2.6 meters. Do we have the time? Yeah. So what's the only thing remaining to get? We got to solve for the force of the motor. So how do we get the force of the motor? Well, look at the elevator here. So what force is down? mg. What force is up? What's the upward force? Force of the motor. Hey, are those two forces equal to each other? Which one has to be bigger? Force of the motor. How do I know force of the motor is bigger? Because it's accelerating. right? The elevator's accelerating, so we have a net force. So you go, okay, let's sum the forces. So we get force of motor minus mg. That's the sum of the forces. This equals ma, right? So take that, solve it for force of motor. You have everything. This ends up being ma plus mg. You could factor the m out, right? We have the a, we have g. So the force of the motor when you plug in comes out as 6,749.145 newtons. So we solve for the force of the motor, plug that in up there, delta x over t, we have everything, right? So look, when you punch all the numbers in, so we got our x, we got our t, when you plug it all in, you're going to get 5,905. 5,905 watts. And the book may have converted that to horsepower. Did they convert that to horsepower? Just if they convert it to horsepower, you divide by 746. 1 horsepower is 746 watts. Okay, now what's another way you could have done this exact same problem? What's the other way to look at power? You could have looked at power how? You could have said, I prefer to do this. Power is energy per time. Well, look, this elevator, as the elevator goes from here to here, what type of energy is it gaining? Well, look, to answer that, let's put a 0 point in. Let's say that here's our 0 point. Does the elevator go above the 0 point? Yes. So it's gaining potential of gravity. What else is it gaining? Kinetic. How do I know it's gaining kinetic? Because it's accelerating. It's speeding up. So this is going to be potential gained plus kinetic gained. So we go mgh plus 1/2 mv squared over the time. And then you plug into this, you're going to get the exact same thing. So we have the mass. We have gravity. What's the h here? 2.625. What's that velocity? 1.75, right? Time is 3. You punch into this, you're going to get the exact same thing. So you could look at it as energy gained per time. Does that make sense? Okay. Now, part B. Okay, so part B, we're now focusing on the second part. So I'm going to show you a couple ways to do this. First of all, I'm going to show you the way that I like. What do we know about the velocity of this elevator? It's 1.75 meter per second. So for part B, the way I would do this, I think it's simplest. Focus on 1 second. Okay? In 1 second, how far is the elevator going to go? What's going to be the delta x in 1 second? Well, how fast is the elevator moving? 1.75 meter per second. So how far will this elevator go? If we focus on a time of 1 second, what's the displacement of the elevator going to be? 1.75 meters, right? It's going 1.75 meter per second. Okay? Now let's solve it. So this is going to be 1.75 meters. So now let's solve this both ways. If we look at this as power is work over time, so this is power of motor, work of motor. So what's the work equation? Work is what? Force times displacement. We're focusing on a time. This time right here, what did we define time to be? We're going to say the time is 1 second. So what's the delta x going to be? 1.75. Now all we got to do is find the force of the motor. Hey, is the force of the motor going to be the same as it was before? Because look at, we have mg down and we have force of the motor up. What's different now? They equal each other. How do I know that these forces are going to equal each other? Because what's different now? What was happening down here? It was accelerating. Now what's happening up here? Constant velocity. So if we have constant velocity, I mean, you could show the whole thing. Sum of the forces. Force of motor minus mg. Sum of the forces always equals ma. But what's our a for this second part? 0. So what's the force of the motor equal to? It's equal to mg. So this is going to give us, I just noticed something. So force of the motor, that's going to be mg times delta x over t. So we have everything now. The delta x is 1.75, the time is 1, so the power of the motor comes out as, wait a minute, where's my answer? Oh, I didn't write it down. What's the answer to part B? Oh, darn it. Well, you punch it in. I didn't write it down, guys. Hey, did I get part A right? Was A right? Okay, so part B, what's the answer to part B? 5,573 watts. Okay, so that's one way of doing it. Okay, what's the other way you could do this? You could look at this as what? What's the other way to look at power? Yo. What's the answer? What does this come out to be? What is it?
Well, if you do your way, you've got 11,147.5.
11,147 watts. Is that the answer? Okay. I apologize, guys. I didn't write out. Normally I write it out, but I didn't put it down. Okay. So you guys can check it. This is the work is correct, so you can check the calculations. Okay. So the other way you could have done this to find the power of the motor during the second part is how? What's the other way? Power is energy per time. Look, now, so what did we have before? In the first part, what we said was the elevator is gaining potential and it's gaining kinetic. So what's different now? In the second part, what's different here compared to there? The elevator's moving at what? Constant speed. Is it gaining kinetic? No, it is not gaining kinetic. So you're going to end up with mgh over t. And notice, this is exactly what we had a minute ago before I deleted it, right? Previously, I wrote mg delta x over t. So you plug into this and you get the same thing. 11,147 watts.